Okay, yes, so the joke is that the next speaker is me. And so I've presented myself. And here we go. Okay, so as you've seen, nanotechnology concerns many different issues. And we can use nanotechnology for many different things. And in my lab as well, we use nanotechnology for several applications, including our collaboration on the project that Kobe just described. But the one particular project that I want to present to you is our effort in trying to restore vision. Now, saying, when somebody tells you that he wants to restore vision, it sounds like a very big statement. And one of the first things I have to do is try to convey that although it sounds like pure science fiction, it's not entirely science fiction. Now, having the capacity to see is clearly very important. And we have incredible capacity, not in the sense of just seeing, but also in our sensitivity to different shapes and colors and perspective. And the reason I'm showing you this particular image is just so you have an opportunity not just to understand that you can see, but understand how much detail you gain when you look at things. On the other hand, seeing seems to be such an obvious thing that often we don't really think about how we can actually gain this ability to see and what are the consequences when we lose this capacity. So usually when we look at our friends and families' eyes, what we see is just the exterior. And some of us may not be familiar with the interior of the eye, which is quite remarkable and actually very similar to a modern camera. So this is a cross-section of the eye. And what we have is a lens, which is actually a very sophisticated one. It can be tuned to select different distances, right? You can choose what distance you would like to focus your gaze onto. At the very back of the eye, we have the retina. The retina is this very fancy layer of cells which is positioned right here and goes all the way almost up to here. Now we have two types of cells that constitute basically the mechanism of vision. So the first set of cells is actually a photoreceptor layer. And you can see that different cells have different colors. And not too surprisingly, you can also recognize the fact that you have these guys, right, which have cone-shaped, and then the rod-shaped cells. And if you know a little bit about the structure of the eye, and you heard this term of cones and rods, you know that these guys actually are sensitive to color vision. And these guys, those colored cones, are actually located at the very center, about right here. This is where the concentration is very high. And this is when we actually have the iris shut down, right? So light comes in when there's a lot of light, not like in the situation right now, but in a situation where there's a lot of light, the iris is closed, light comes in and hits the central part of the retina. On the other hand, when the light is dim, when there's not much light, the iris opens up, the eye collects, like a good camera, collects a lot of light, and this light actually reaches the other parts of the retina. And this is where we have a lot fewer cones, but then we have a lot of rods, and these are very sensitive cells. So this is the mechanism. It's very complicated and very fancy. And once light hits these cells, the information from these cells is transferred forward to these cells. These are actually neurons, and the extension of these neurons goes collectively into a fiber, which is basically the optic nerve, and the optic nerve eventually reaches the brain, and this is how we can see. So if we look at this letter here, A, other than ignoring issues of what happens at the lens, so Kobe will forgive me for not being completely accurate, but the information goes in, basically flips, but basically hits the retina, the information from here goes back here and then goes to the brain. Now that you know how the eye is working, you can imagine what would be the consequences of deterioration of this layer. The result is basically catastrophic. The result is blindness. And the problem with this thing is that this is not very rare. This is actually one of the major cause of blindness, and this is what happens in AMD, age-related macular degeneration. And as the population ages and people reach longer and longer age, basically one of the challenges is that particular situation. And there are many related situations which also affect very young people. So it's a significant issue of vision loss that is related to that one particular problem. So blindness, as we can all appreciate, is a very, very severe issue. Of course, it limits us tremendously, but we may not appreciate the fact that over 80% of our daily activity actually depends on sight. So it's not that you cannot have life without seeing, it's just that you lose a lot of the interaction and the interfacing with the external world. And the other thing, as I said, this particular case of retina degeneration is a very major cause of blindness in aging population specifically, but not just. And the sad thing, just as was mentioned in some other examples, there's no cure at the moment. And people have been working for many years, and people are trying to find a cure. So you can cure such a thing, or you can approach such a challenge using biological approach, just as was presented before. But you can also try and use technology. You can also try to use solid-state technology or electronics to solve the problem. And what can be done and what has been suggested, and this is the point where I try to convince you that this is not entirely science fiction. These are two examples from two companies, an American one and a German one. They've developed an implant. Here it's one particular implant. This is a second type of an implant that is inserted into the eye. And those of you old enough to remember Steve Austin, this particular device also have better sensitivity at the infrared range. Okay, so this guy could actually have infrared vision. Now, the kind of performances, and these images that you see here are actually implants in human eyes. These devices have been around for quite a long time. There have been patients, some patients with such implants for several years, and people can regain vision, very, very limited one, but they can regain vision using these technologies. This particular company already have a CE mark, and they can sell their product in Europe. So we have the technology, but not at the level that we want it to be. So what we're doing in the lab is actually trying to come up with better technologies to address that particular issue of interfacing with neurons, stimulating neurons, and being able to restore vision and possibly other examples. So what you see here is an example of something we do quite routinely in the lab. But just as Roy said, when we say we, it's not really we. It's Nitzan or Ad or somebody else who does the experiment, but it's definitely not me. But these are neurons that are sitting on electrodes, and we can use very, very fancy techniques to record the neurons and interface with them. So we can actually work quite systematically in the lab and do these kind of things. We can stimulate neurons. What else we can do? And here comes the nano. So we can take nanomaterials, and in this particular case, again, these are the carbon nanotubes, and we can, again, take neurons, and we can look at how neurons interface with these nanomaterials. And one of the things that we noticed a long time ago when we started this research was that there's a lot of love there. Neurons actually love such surfaces. Now, why would neurons, right, the stuff that we have in our brain or in the retina or in the edges of our fingers, Why would they care about carbon nanotubes, a material which was discovered only in 1991? I mean, how could possibly they have affinity for such a material? Part of the reason they don't really care about the material, but they really care about the topography. And this particular topography is very similar to what cells actually encounter in the biological systems. Just as we showed to you, there are a lot of fibers around, lots of very, very elongated things. So these are just nice elongated things, okay? So neurons like them, but we like them as well. The reason why we like them is because this is actually a conducting material. So we can connect it to stimulator, and we can actually drive current through it. So this is a perfectly electronic material. Just as Colby said, we can use carbon nanotubes to do solar cells, okay? So cells like them, we like them. Let's try and put these things together. So we had to work for a while to come up with a method how to take these very, very fluffy, strange material and turn it into electronic circuit. Something a little bit closer to what we have inside computers or any electronic device. We can do that. We can develop processes, again, using very, very fancy equipment that we have at the Nano Center. And again, we'll be very, very happy to show how these things look like. But we can take these materials and somehow, using a very special, specially tailor-made process, grow these nanomaterials, these hair-like structures, right here when we want them on the electrodes. So we did that, and we investigated how these things work, and we were very, very happy about that. And at some point, we started thinking very seriously about taking these materials, taking these devices, and introducing them into the biological system. Right? We have a material that the neurons like, we like this material, we can work with it. It's a win-win situation. But this wasn't enough, right? Because at first, when we said, let's take this technology, let's take this material and put it on use electronics to build these materials, we ended up building our systems on silicon, right? It's exactly the same material that we use to build computers. Now, silicon is rigid, okay? And a rigid material is not the best material if you want to put it into a biological system. Biological systems don't like solid, rigid materials, at least not when they're big ones. So we had to come up with an alternative. And one of the alternatives, and it took us a lot of time to find the exact way how to do that, but conceptually the idea was we want something like this. We want this material that the neurons like so much. You see all these little hairs, but we want it to be on a flexible material. So these are actual devices that we have in the lab. It took us a lot of time to figure out how to make them. And then we figure out a way how to make them, but then we realize it doesn't come out very well. So it took us some more time to figure out the right way how to make them. And then it took some more time to figure out how to test them. But eventually, we were able to do all that and to come up with devices which are perfectly flexible, right? We can make any circuit that we'd like because we're still using a technology which allows us to make any kind of circuit. And we can do electrical recording and electrical stimulation from biological systems. So we started initially by studying neurons in the same way that I told you before. We would just take neurons from, say, rats, and we would place them on the electrodes, and we would test them and look at the response. And then more recently, we started using retinas that we're putting directly on these electrodes, and we can record them, and we can work with them. And we can really convince ourselves that these things basically do everything we wanted. They're flexible. They have these fantastic surfaces that the neurons like so much. They have these conducting materials that we like so much. And at this point, it seems like a win-win situation for everybody. So the last thing we had to make sure is that if we look at the biological system, right, the retina itself, that the retina would be happy. Now, in order to see whether the retina is happy, we can approach this in several different ways. One way is to actually take implants and put the implants into eyes. And we do that already, but this is something you start only because to do that, you need to involve animal testing, and this is something you try not to do unless you really have to, and you really sure that you have something significant. So before we started doing that, we actually worked with retinas that we took away, basically peeled off retinas and put the retinas on our carbon nanotubes. This particular test was actually done by colleagues at the University of Newcastle in England. And you can see here a cross-section with a resolution. This bar here is 500 nanometers. These are our carbon nanotubes, 20 nanometer in diameter. And this is basically the retina after 2 days completely engulfing the carbon nanotube layer. So the same effect that we had simply by running a test where we take neurons and try to interface them with carbon nanotubes, we obtain by taking an entire retina, placing the retina on the carbon nanotubes, letting it stay, keeping it alive, and seeing the interaction. As I told you before, we also do the same thing by putting the flexible devices into real eyes in an animal, and we see similar results, very encouraging results, that we can have a very nice and intimate contact between the retina, between the biological system and the artificial system. So what does it mean? It means that we have a new material with complete integration into a complete system that we can combine with the retina and achieve much superior interface than simply taking an electronic device that was designed to work in a computer and just put it into the eye, which is basically pretty much what the rest of the world is doing at the moment. So this is where we're standing at the moment. And just to summarize, now that you know a little bit more about the eye, this is actually a part of a very, very insightful poem by Rumi about, he's talking about God and other things, but just one piece of information that now you have, and you may have not realized it before. Now you know that when lights are, especially at night, you don't really see colors. Your vision, right, relies on the rods in the eye, and basically your ability to distinguish between different colors is quite diminished, and you're blind. And this is what Rumi was saying about the significance of God being able to see the different colors. So this is how beautiful the eye is, and how important it is, and how much we have to fight to find ways how to cure those particular challenges. And thank you very much. That's it.